F1 cars stick to the track at mind-boggling speeds, and it all starts with their wings. But why are they upside down, multi-layered, and full of slots? Today, we're breaking down every single detail of Formula One wings, explaining why each tiny flap matters for speed, grip, and ultimate performance. So, let's start with the most fundamental question. Why are F1 wings upside down? If you look at an airplane wing, there's a distinct curved surface along its top side and a smoother, flatter surface along its bottom. Now, a popular explanation for how airfoils generate lift is that air traveling over the top has a longer distance to cover and must speed up to meet the air underneath. This sounds intuitive, but it's actually not how lift works. We won't go deep into the math here, just enough to understand why flipping the wing works. Airfoils actually generate lift through two main mechanisms. The first is related to airflow curvature. Because air follows the curved upper surface of the wing, it is compressed as the curvature channels the flow through a smaller effective area. According to the continuity equation of fluids, when airflow is forced through a smaller area, its velocity must increase to maintain the same mass flow rate. This increase in velocity, as described by Bernoulli's principle, causes the pressure to decrease, generating a pressure difference between the top and bottom surfaces of the airfoil, with lower pressure on top and higher pressure underneath. It produces lift. The second mechanism comes from Newton's third law. For every action, there is an equal and opposite reaction. As airflow leaves the trailing edge of the airfoil deflected downward, it imparts an upward reaction force on the wing, further contributing to lift. Now that we understand how lift works, we can move to Formula One. An F1 wing is essentially an airplane wing flipped upside down. Its job isn't to lift, but to do the exact opposite, push the car down onto the track. This is called downforce. By inverting the wing shape, all the same aerodynamic principles apply, just in reverse, generating downforce instead of lift. This downforce acts like a giant invisible hand, pressing the car firmly into the asphalt, dramatically improving stability and, more importantly, grip. It's also important to note that downforce scales with the square of speed. That means as velocity increases, downforce rises extremely quickly. This is why F1 cars generate enormous downforce at high speeds, but almost none when stationary, making them incredibly difficult to launch off the line. At around 250 kilometers per hour, an F1 car's wings can generate forces comparable to a small truck sitting on top of the car, and all of that disappears the moment the car slows down. In fact, an F1 car produces so much downforce that, in theory, it could drive upside down on the ceiling of a tunnel, as the aerodynamic forces exceed the car's own weight. It's this incredible force that allows drivers to take corners at hundreds of kilometers per hour without sliding off the track. Without it, the car would simply lose grip and fly off at the first high-speed bend. However, there's always a trade-off. Generating downforce also creates aerodynamic drag, a force that acts opposite to the car's direction of travel, resisting motion and reducing straight-line speed. So engineers are constantly battling to find the perfect balance between maximum downforce for corners and minimal drag for the straights. And these decisions are highly track-dependent. If you look closely at the ends of an F1 wing, you'll notice two vertical panels called end plates. These play a crucial role in making the wing efficient, particularly in terms of downforce to drag ratio. High-pressure air on top of the wing naturally wants to spill over into the low-pressure region underneath, much like how air moves between pressure zones on a weather map. When this happens, it creates swirling vortices at the wingtips. These vortices represent wasted energy. They disrupt clean airflow, reduce the pressure difference across the wing, and ultimately rob it of downforce. This is known as induced drag. End plates act as barriers, limiting this spillage. They minimize the strength of these vortices and move them further away from the critical sections of the wing. This allows the wings to be more efficient in downforce generation, Without them, much of the wing's effectiveness would be lost to chaotic, spinning air, making the car slower and less stable. End plates also help guide the dirty air coming off the wing in very specific ways to improve the aerodynamics of the rest of the car. But wait, it gets even more complex. You might have noticed that many of these end plates aren't solid panels. They have intricate slots, louvers, and holes cut into them. These aren't just for looks. These slots allow a small, controlled amount of high-pressure air to bleed from the inside of the end plate to the outside. This controlled bleed energizes the airflow, helping to keep it attached to the wing's surface, and further minimizing the strength of those energy-sapping wingtip vortices. Additionally, since the end plates run from the top to bottom of the wing, they are also subject to a pressure difference across them. This means that they themselves produce swirling vortices that contribute to induced drag, just to a lesser extent. By bleeding the air across the end plates, the strength of these vortices can be managed and induced drag reduced. Even tiny adjustments to the shape and position of these slots can have a measurable impact on performance, potentially shaving tenths of a second off a lap time. In a sport where thousandths of a second can mean the difference between winning and losing, this level of detail is absolutely critical. It's a perfect example of how F1 is a game of marginal gains, where every single component is optimized to the absolute limit. Let's dive even deeper. Modern F1 wings are never just a single, simple airfoil surface. They are always multi-element wings, meaning they are made up of several smaller wing profiles, or flaps stacked one behind the other. If you look at a front or rear wing up close, you'll see it's a complex assembly of 2, 3, or even more individual elements. I mean, just take a look at this front wing from 2018 and how many individual elements it's made of. Why do they do this? Stacking elements allows engineers to generate more downforce from a wing of a given size than a single element ever could. Each element works like a mini-wing, generating its own little pocket of low pressure. The gap, or slot, between each element is crucial. It allows high-pressure air from the top of the previous airfoil to flow through and re-energize the air moving underneath the next element. This prevents the airflow from detaching from the surface, courtesy of the adverse pressure gradient, a phenomenon called stalling, which would cause a sudden and dramatic loss of downforce. By carefully shaping each element and the slots between them, designers can create a much more powerful and efficient downforce generating system. But of course, there's no such thing as a free lunch in aerodynamics. Whenever a wing produces lift or downforce, it also produces a type of drag previously mentioned, which is induced drag. This is the drag that is an unavoidable consequence of generating downforce. It's caused by those wingtip vortices we talked about earlier, the swirling masses of air that spill off the wing tips. These vortices represent energy that is being used to churn the air rather than to push the car forward. The more downforce a wing creates, the stronger these vortices become, and the greater the induced drag. This creates the classic F1 setup dilemma, and it can be directly seen in how teams decide on their rear wings each race weekend. Low downforce wings prioritize straight-line speed, while high downforce wings trade that speed for grip. In this image, you can see the two extremes: Monaco on the left with the highest downforce wing of the season, and Monza on the right with the lowest. Quite the difference, right? And that's the challenge engineers are always chasing, finding the sweet spot between enough downforce for the corners and minimal drag on the straights. Nailing that balance is the key to unlocking lap time. This is why pre-race simulation and practice sessions are so important to teams, as without them, getting the setup and tuning of the cars correct would be like trying to win a chess match blindfolded. Every move matters, but you don't know the consequences until it's too late. So, from inverted airfoils that suck the car to the road, to multi-element flaps that multiply grip, and intricate end plate slots that manage every wisp of air, every single part of an F1 wing is a masterpiece of engineering. Each tiny tweak and adjustment is meticulously designed to influence speed, cornering stability, and ultimately lap times. Next time you see an F1 car seemingly defy physics as it sweeps through a corner at 300 kilometers per hour, you'll know one of the aerodynamic secrets that keeps it glued to the track. Thanks for watching. If you enjoyed this deep dive, make sure to like and subscribe, and leave a comment with any engineering concepts you'd like broken down in future videos.